Hi everyone, so today I'll be proving that square root of 2 is irrational using proof by contradiction. So in order to prove that this statement is true, using proof by contradiction, we first have to assume the opposite, right? So I already wrote it down where we're going to assume that square root of 2 is rational and can be written in the form p over q, since rational numbers can be written as fractions, and both p and q belong to the integers with no common factors between them. This part is important, and we have to assume that the fraction is in its simplest form and basically can't be reduced. So I'm going to start by writing that square root of 2, this is the first step by the way, we're already starting. Square root of 2 is equal to p over q, and I'm going to square both sides. So square root of 2 squared equals p over q whole squared, and then the square root and squared gets cancelled, so I'm left with 2 equals p squared over q squared. I'm going to bring the q squared to the left side and get 2q squared equals p squared, and now I can see that because the q squared is multiplied by 2, that's showing me that p squared is actually even, right? Since any number multiplied by 2, basically any multiple of 2, is even. So therefore p squared is even, and any number when you square it and the answer is even, then the original number has to be even also. So since p squared is even, p is even. And then because p is even, I can replace p, and when you want to represent an even number, you can write it as 2 multiplied by some integer, let's say in this case k. So p will be 2k in this case, and I'm going to replace it over here. Let me just remove that so there's not too much scribbles. And I'm going to write it as 2q squared equals 2k whole square, and then open the brackets, so I get 2q squared equals 4k squared, and then q squared will be equal to 4k squared over 2, the 2 gets cancelled, and then I have q squared equals 2k squared. And now I basically reached the same point here that I did here, and this is going to show me that q squared is also even, since it has a 2 multiplied with the integer k. So I'm just going to remove that, because q squared, you don't have to write this part down exactly since we already showed it here and also showed it here, and these two are basically the same thing but showing for both p and q, but I'm just gonna write it so that it's more clearer. So q squared is even, so q is also even. And now, because both p and q from here are even, right? That means that they both have a common factor of 2. And if the fraction has a common factor of 2, that means that it contradicts the original statement where we said that p and q have no common factors between them. So that's actually going to be our conclusion. So I'm going to have this. This is the symbol for therefore. So therefore, p and q, I'll start with this first. P and q are even, having a common factor of 2. This contradicts the original assumption that they have no common factors. And now, therefore, square root of 2 has to be irrational, right? Because it can't be written in this form. It cannot be written as p over q. So therefore, square root of 2 is irrational. And I just want to point out one more thing also. We proved at this part that p squared is even, so p is also even, right? And now I just want to show you one extra thing. So p squared is even, p is even. And actually, I'll do a small proof of this as well to show that any number squared, any even number squared, the original number is even, and any odd number squared, the original number is odd. I'll do a small proof for that, but I just wanted to show what happens when we try to make p odd instead of even. P is even, but I just want to show what happens when we try to make it odd. So if p would be odd, that means instead of representing it as 2k, we would make it as 2k plus 1, right? So let's say p is 2k plus 1. That means for p squared, it would have to be p squared, it would have to be 2k plus 1 squared, right? And that's gonna give us, first square the first term, double the product, square the last term. And now we have this, and we can factor out 2 and get 2 bracket 2k squared plus 2k plus 1. And now again, it's basically the same thing as this, where we have 2 multiplied by some integer plus 1 to show that it's odd. So that just shows us that p, when we have p is odd, p squared is also going to be odd, contradicting what we said over here, that p squared is supposed to be even. So that's how we know p squared is even for sure. That's just one more extra thing I wanted to show. But anyway, yeah, that's pretty much it for this one, and I'll do another example with square root of 5. This whole process of proof by contradiction works for basically any square root, like square root of 2, and yeah, I'll just do one with square root of 5. So first, basically, we would just start with the same assumption. I'm not going to rewrite it again, but all the points are the same. It's rational, can be written in the form p over q. This time I'll take a over b, and there's no common factors between them. So let's say square root of 5 is equal to a over b. And then again, I'm going to square both sides. So a over b squared is equal to 5 is equal to a squared over b squared. And then I'm going to move the b squared that side, and I'm going to get 5b squared equals a squared. And then I'm going to move the 5 back down there actually, and you'll see what happens. You get b squared equals to a squared over 5. And now we know that a and b are both supposed to be integers, right? But over here, b squared is, since b is an integer, b squared should also be an integer. But over here, I see that it's a fraction, a squared over 5. So what this means is that a is actually supposed to be a multiple of 5, so that this whole thing is perfectly divisible by 5, and I can get rid of this 5 right here. So because now we know that a should be a multiple of 5, I can rewrite a as a equals, let's say, 5k, for example, where k is again some random integer, and then replace that in this. So I get b squared equals 5k squared. Oh, sorry, looks a little wonky. 5k squared over 5, open the bracket, so I have, I'm just going to bring it down here, b squared equals 25k squared over 5. The 5 gets cancelled, and I'm left with b squared equals 5k squared. And now I'm basically going to reach the same point that I got here to show that b squared is also a multiple of 5, and along with a squared also. So I'm going to bring the 5 down here, and that just shows that b squared over 5 is equal to k squared. So now because this is also supposed to be an integer, right? That just shows that b should also be a multiple of 5, so that this is perfectly divisible and this denominator of 5 gets removed. So I can rewrite, well, actually, no, I don't have to rewrite at this point. Like, we understand that b is also supposed to be a multiple of 5 since we already wrote it down for a. So I reached my conclusion, actually, that b is a multiple of 5. And a is a multiple of 5. This contradicts the original assumption that there are no common factors between a and b. So therefore, root 5 is irrational. So that's pretty much it to this whole process. I'm just going to do one last quick proof to show that any even number squared is going to be even and any odd number squared is also going to be odd. I basically showed it here. Actually, like, it's very much a similar thing. Like, it's the same thing, but I'm just going to write it out again. So this is the proof for any even number squared is even and any odd number squared is odd. So first, I'm going to start with writing an even number, which is represented by p, and then I can say it's going to be 2k, where k belongs to the integers. It has to belong to the integers, because it has to be a whole number, but it can take a positive or negative value. And then I'm going to square both sides, similar to the proof. P squared is equal to 2k squared, which gives me 4k squared. And now I'm going to factor out that 2 from the 4, and I get 2 bracket 2k squared. And now it's basically the same thing as this, right, where I have 2 multiplied by some integer. So because 2k squared is an integer, that shows that any even number, when you square it, it's going to give you an even number since this is a multiple of 2. So yeah, that's basically it. And then for odd numbers, it's basically the same thing. Instead of 2k, it's going to be represented by 2k plus 1, like I already did that here. So I'm going to take, let's say, q and make it 2k plus 1, and then square that. So I get q squared equals 2k plus 1 squared. And then when I open the brackets, it's going to give me the, you first square the first term, 4k squared plus 4k plus 1. Take 2 out of this whole thing, factor 2 out of it, so that gives me 2 bracket 2k squared plus 2k plus 1. And then we reach the same thing here originally, where we said that it's 2 multiplied by some integer plus 1. Over here it's also 2 multiplied by some integer plus 1. So that just shows us also that any odd number, when you square it, it's also odd. And yeah, that's it for this whole thing. I hope you understood. Thank you so much, and bye.